Number 10, figure 5 represent a equipotential surface and electric field E near to the positive charge Q. So this is a positive charge Q at the center. And number A, from the figure, give the three relation between equipotential surface and electric field. If you look at the figure 5, so this is positive charge. This is positive. So meaning the positive charge will produce the electric field is direction outward to the center. This is direction outward to the center. And the next is the direction of electric field E is always 90 degree to the equipotential surface. So this is equipotential surface. And if you see the figure 5, this is a positive charge Q, and if you look at the E here, let's say E at the point A, at the point B is the magnitude E at the point A, and magnitude E at the point B with the equipotential surface. E at A is greater than E at equipotential surface at point B, because EA is near to the charge Q. Number B, calculate work done by electric field on 3 microcoulomb test charge that is displaced from A to B. So now at the point A here, at the point A, this is equipotential surface. The potential at VA is 300 volt, and at the B, V at P is 200 volt. So meaning the work done, as you know, the work done equation is Q times delta V. Sorry. W is equal to Q delta V, and the Q here is the charge 3 microcoulomb from A to B. So this is 3 microcoulomb, and the delta V here is a change of from A to B, meaning VB minus VA, and the VB is equal to 200 volt, and the VA is 300, meaning the 3 microcoulombs times, say the 3 microcoulomb, so the W here is 3 microcoulomb times 200 VB minus 300. So the work done is equal to negative 3 exponent minus 4 joule. And number 3, so number 2, work done from A to C, from A to C, but from A to C is, this is on the A to C is on the same potential, right? A to B is a same potential or equipotential surface, meaning if you have the equation Q delta V, because the V at A and V at A the same value, meaning this is equal to 0. So work done from bring charge A to C is equal to 0. Next is number C. If the charge Q, so the charge Q is charge Q here is 5, this is nanocoulomb, or this is nano is 5 times 10 power of minus 9 coulomb. Calculate distance between point charge Q and A. So what is the distance here, right? R. So as you know, the equation for the electric potential V is given by the K Q over R. And now the value of the K is constant, 9 exponent 9, and the charge here is magnitude is a 5 exponent minus 9 coulomb, and V at that point A is given by the value 300 volt. 300 volt. So now you can find the R or distance here. Right? So the R, use the calculation here, you can find the value of R is 0.5 meter. And next question is calculate electric field at the point A here. So what is the electric field at the point A? As you know, the electric field E equation is K Q over R square. So now that you find the distance from Q to A here, this is answer number 1. This is 0.15, this is square, and the K, as you know, K is constant, 9 exponent 9, and the Q charge here is given by the question is 5 nanocoulomb. So it's easy for you to find the value of E. So the E is equal to 2000 Newton per coulomb. And number 3, a new charge, this is negative charge, 5 nanocoulomb is placed near to the Q. And sketch where this new charge could be placed, such as the potential at the point A is equal to 0, and explain your answer. So at the point, you have another charge. Let's say we have this is point A, right? This is point A. So now we have let's say Q here is a positive 5 nanocoulomb, and we have another charge. Let's say this is Q2, same magnitude, but this is negative nanocoulomb. And now if you, as the question said, the potential at the point A, because of two charge Q1 and Q2, the potential at VA is equal to 0. And as you know, the equation to calculate the potential of the VA is a K magnitude charge Q and R. So meaning you can find the distance here because the K is constant. K is constant, okay, 9 exponent 9. But the charge here, because if you calculate the potential, electric potential, you must use a negative sign because Q2 is a negative and the Q1 is a positive charge. So meaning if the potential at the point A is equal to K, Q1 is a positive over R, and we have another is a K, Q2 is a negative charge over R. So this is same magnitude, but this is a negative, so meaning VA here is equal to 0. Potential at VA is equal to 0. And the last question is, if the point charge Q is replaced by negative point charge is equal to magnitude, describe the change in the equipotential and electric field. Right? So what happens here is so now this is we start from the positive charge, meaning you have a positive charge, right? Electric field produced by the positive is outward. But if you use the negative charge, the direction to the inward, right? Inward negative charge. So you have the positive, this is positive. If you change Q is a negative, so it's the electric field. And what happened if you use the negative charge, the equipotential surface here, let's say this is a, use a negative charge here. So equipotential surface, the value here is a negative, right? At the V at the A, V at the B, V at the C, we use negative, the value of VA, VC, VB is a negative value. That's all.